Right, this is the morning review for quiz 3.1 to 3.4. Okay, so here's our function. We want to know whether Rolle's theorem applies to this function between the closed interval from 0 to 6. If yes, find the value of c defined by Rolle's theorem. First thing we need to check is to see whether our function is continuous and differentiable on the closed interval. If we look at the original function, we see that the denominator will have a vertical asymptote at x equals -2. So we know there's a break in the graph, but that break in the graph is not going to is going to be outside the closed interval from 0 to 6. So we're safe there. The next thing we need to check for is whether the function is differentiable. The way we do that is we find the derivative function and look to see if we can determine whether there's any points on the graph where the derivative is undefined. So we go through quotient rule. So f prime g minus fg prime all over g squared. We expand, and if we keep expanding, we're going to be able to factor. We get x plus 6 times x minus 2 all over x plus 2 quantity squared. Again, the only x value that we see that's giving us issues is at -2, and again, -2 is the vertical asymptote, and that's why the function is not differentiable there, but that is outside the interval from 0 to 6, so we can say our function is continuous and differentiable on the closed interval from 0 to 6. All right. The third condition for Rolle's theorem is whether or not the endpoints will produce the same y value. What Rolle's theorem is trying to do is it's trying to guarantee that somewhere on the curve there's going to be a slope of the tangent line where the slope of the tangent line being equal to 0. Now, to guarantee that, the endpoints have to also produce the same y value so that the average slope will produce 0. So we plug our endpoints 0 and 6 back into the original function. When we do that, we'll get 0 minus 0 over 2, which is 0. If I plug 6 in, I'll get 36 minus 36, 0 over 8, which is still 0. So here we see that the endpoints produce the same y value, and if we find the slope, we get 0 over 0 minus 0 minus 0 over 0 minus 6, which is 0. So our average slope is 0. If our average slope is 0, we can guarantee that somewhere on the curve there's another point, at least one other point, where the slope of the tangent line is also 0. So we've set our derivative equal to our average slope, and if we do cross product, we're going to get x equals 2 and x equals -6. Now, -6 is outside the interval, so the only x value that we can guarantee is at 2, so c is equal to 2. Number 2, determine whether MBT can be applied. So first thing, again, we need to check to see whether the function is continuous and differentiable on this closed interval. So for continuity, we can look at the denominator of the original function. We see that there's an x there, meaning that there's a vertical asymptote at x equals 0. But 0 falls outside the interval from 1/2 to 2, so we know that's not going to, the vertical asymptote, the break in the graph, is not going to affect the region that we're looking at. Now, to determine differentiability, we're going to have to find the derivative and see if there's any other denominator value that we have to consider. So with x plus 1 over x, we can go through quotient rule. So f prime g minus fg prime all over g squared. And we clean this up, we get -1 over x squared. Again, the only denominator value that's that the function is not differentiable is at 0, and that's the same value where there's a vertical asymptote. So again, that is outside the interval, so we don't have to worry about that. We know the function is continuous and differentiable, therefore, between our closed interval from 1/2 to 2. Now, what mean value theorem does is now it's going to be able to guarantee that whatever the slope is between the endpoints, that slope, there must be another point on the graph, on the curve, where the slope of the endpoints has to be shared somewhere on the curve. So now to find the slope at the endpoints, we're simply going to plug 1/2 and 2 into the original function. And if we plug 1/2 into the original function, we'll get 3. If we plug 2 into the original function, we'll get 3/2. We do slope of the secant lines, the average slope, so change in y over change in x. y sub 2 minus y sub 1 over x sub 2 minus x sub 1, and this cancels out all the way to negative 1. So the average slope is negative 1. Somewhere on the curve, there's going to be at least one other point where the slope of the tangent line to the curve is equal to negative 1. So to find that, we're going to set our average slope equal to the derivative function to find the location where this slope of negative 1 will occur on the curve. So we do cross product and we solve for x. We get x equals plus or minus 1. Now, negative 1 falls outside the interval, so we have to take that out. The only x value that we can use is what's in between 1/2 and 2, which is 1, so c value is equal to 1. Right, number 3, use the second derivative test to classify the critical points of f of our function. Now, the second derivative test is using this f double prime to find relative extrema. So this is not the test to find concavity or points of inflection. This is using the second derivative function to determine relative max and relative min. This essentially does the same thing that the first derivative test does, just using a different method. So we need to first find our f prime. So we go through power rule. We get 1/4x cubed minus 6x squared. 6 goes to 0. So we can simplify and factor out the x squared, and we get x equals 0 and 6. Now these are the critical points that are the candidates for relative max and relative min. Rather than making a sign line and testing the intervals to see whether the slope is increasing or decreasing, we're going to be using the second derivative function to determine whether these values are relative max or relative min. Okay. So let's move on to the second derivative. So x cubed minus 6x squared is f prime. We find the derivative once again to get to f double prime. We get 3x squared minus 12x. 6x squared becomes negative 12x. Now we're not going to factor and solve for x, because then we would then be looking at critical points for points of inflection. But we're only using this function to plug in these candidates for relative max and relative min. So first thing we do is we plug 0 into the derivative. Second derivative, we're going to get 0 minus 0. Now this is going to be inconclusive because 0 is neither concave up or concave down. So this means that this second derivative test is not sufficient to determine whether at 0 there's a relative max, relative min, or neither. So we have to leave it at like this. We can't say anything conclusive about x equals 0. So let's now plug in 6. If I plug in 6 into the second derivative function, we'll get 3 times 6 squared minus 12 times 6, which combines to be 108 minus 72, which is 36. 36 is greater than 0. So we know at 6 the slope is 0, and we also know that at 6 the graph is concave up. If the slope is 0 and the graph is concave up, then it must be part of a graph that looks like this. And if it looks like this, where the graph is concave up on the point where the slope is 0, then we know that there must be a relative minimum at x equals 6. Okay, number 4, sketch a labeled graph with the following characteristics. We have ordered pairs here, so I'm going to go ahead and plot them at -1, 4 and at 2, -1. We have information about the first derivative function, so I'll make a sign line there. Positive slope to the right of to the left of -1 and to the right of 2, so positive slope. And then negative slope, f prime is less than 0, between -1 and 2. Right. We know that there's a point inflection at 1, 2, so we'll make a second sign line for f double prime. We have second derivative is negative to the left of 1, so concave down. F double prime is greater than 0, so concave up to the right of 1. So we want a graph with these characteristics and a point of inflection at 1. So we can choose any y value we want, but you want to have this basic shape. We basically want a relative max at -1. We want a relative min at 2. Point of inflection is at 1. And we want the graph to have that characteristic where it's concave down followed by concave up. Okay, one more problem. Number 5, find the absolute max and absolute min of the function on the given interval. Now, if we want to use extreme value theorem, which is allowing us to find the absolute max and absolute minimum on the closed interval, we need to first determine that the function is continuous everywhere. So we see that in the denominator, there's not going to be ever any value where the graph, where x is not going to exist. So we can say that our function is therefore continuous. There's no need to state anything about differentiability. So as long as the function is continuous on the closed interval from between our endpoints, then we can guarantee that there will be an absolute max and absolute min, at least one absolute max and at least one absolute min on the closed interval. Okay. Now, the candidates for absolute max and absolute min are the endpoints. So we're going to have to definitely test -4 and 4, and also the critical points. Now, critical points is going to come from the first derivative, either where where the slope is 0 or whether the slope is undefined. So we're going to have to consider critical points that can come from numerator of the f prime or the denominator of f prime. So to get to f prime, we need to go through our appropriate rules here. We can go through quotient rule. So f prime g minus f g prime all over g squared. We can expand, and if we expand all the way, we get 16x over x squared plus 4 quantity squared. Critical point from numerator will just be 0. 16x equals 0, so x equals 0. And denominator, we're never going to be able to set this equal to 0. So x will produce an imaginary number, so we know that no critical point will come from the denominator. So we have one critical point from f prime, and we have two endpoints, so we have to test all three back into the original function and just compare the y values. So -4 gives us 12 over 20, which is 3/5. Plug 4 back into the original function, and that will also give us 3/5. Plug 0 back into the original function, and we'll get -1. So therefore, we have 3/5 is greater than -1. We have a shared absolute maximum at 3/5, and we have a absolute minimum at -1. So we can say absolute max is 3/5 at -4 and 4. Absolute minimum is -1 at x equals 0.